Put it away, Darian.
All right. Welcome to day 2 of VSEPR. If you remember, yesterday we started drawing molecules. Hopefully you're getting good at it. Today is not much different. I just want to twist a tiny little item that can happen on some of your drawings. But before we do that, as promised, I want to comment on metallic bonding. So do me a favor in your packet and go to the back of page 1. The back of page 1. If you look near the bottom of the back of page 1, you'll see a blurb about metallic bonding. So I want to elaborate a little bit about what it refers to. Metallic bonding is a metal bonding to a metal. It's actually the only combination we didn't talk about so far, right? Because we have metal to nonmetal is ionic, non-metal to nonmetal is covalent. So metal to metal is metallic. Most of the time in here, when we talk about metallic bonding, we're talking about a metal atom bonding to a copy of itself so many times that it creates a metal sample, like this one. What do you think this metal's made of? Aluminum? What do you think it's made of? Steel? Now, steel's not an element, is it? Is steel an element? It's not. Steel's an alloy. So that would be a slightly different example than what I want to talk about today. So let's just say it's made of silver, even though it's not pure silver. If this were made of silver, what it would be made up of is a bunch of silver atoms bonded to each other. Silver, 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 silver. So many of them bonded together that it creates this silver bar. Now, if you were to take an electron microscope and zoom in as far as you could on this metallically bonded item, it would look like this. Here's the cool thing that metallic bonds do. Let's say this is one of the silver atoms, right? And there's another one, and there's another one. When the silver atoms initially come to the bond to form it, they bring their valence electrons with them. But unlike other types of bonds, once the bond is formed, the metallic electrons are able to delocalize. Now think about what that means. If something's local, that means it's in its own area, right? It's in its own neighborhood. If you are delocalized, then it means you have left the neighborhood. Like right now, y'all are all delocalized because you're not at home. Once these electrons, or rather metallic atoms, bond together, their electrons not only delocalize, but they are able to swim to other areas of the created metal. And it's just metallic bonds that allow this, to the point where when you get a whole bunch of them put together, there's electrons swimming all over the place that don't actually belong to the metal atoms that are in that area. This sea of electrons, as we call it, leads to some of the metallic properties that you know metals have. For example, let's say that this was a hot plate. It's not, but let's say it was. And I pump the hot plate all the way up, and I take this metal sample made of metallic bonds, and I rest it on the hot plate. What do you know will eventually happen to my metal sample? It'll get really hot. But why? Why do we cook with metal pans? It's because of this. The reason that metals are so conductive is that if I put this on the hot plate, at the point of contact, there were electrons there around those metal atoms. But what were those electrons about to do? They were about to delocalize. They were about to swim away. So when it got hot, those electrons then started swimming to a different area of the sample, and new electrons swam to the point of contact. Then those absorbed some of the heat, and they swam away, and new ones swam to the point of contact. Then they swam away, until eventually the ones that are delocalizing so far from that source make it down to my hand. And what do I feel? The heat that has now made it down to me. And if it stays there long enough, all of those delocalized electrons will absorb the energy, and the entire metal sample will get hot. So it's the sea of electrons that leads to some of these metal properties that we've already covered in previous units. I can ask you questions about that idea, so at least circle that area in that packet if you didn't write anything down during that little spiel. Where's my pencil?
Right there.
Are you a good talker?
Oh, you guys again! You should have been lefting. All right, y'all, so let's finish our unit with a slightly tweaked version of our drawing. So focus back in. We're going to draw 3 molecules today. No. For those of y'all at home, right now, make sure that you have your stuff out. You'll need your packet, a polyatomic list, and a periodic table. Whoops. And the screen says arsenate. So let's talk about arsenate.
How do you create fire? Like what elements create fire?
Do you agree that that is arsenate? All right. So when you see arsenate, you should look at your polyatomic list or your brain if you are a respectable individual, and you'll see that that is arsenate. I know that the polyatomic ions are made up of covalent items because they're all non-metals. But even though the polyatomics are built covalently, so VSEPR applies, they bond ionically. So that's kind of what's interesting about them. But the drawings follow yesterday's rules. So let's get back in the groove. Ready? Step 1, I need a valence count. Arsenic is in group 15, so he's got 5 valence electrons. Oxygen is in group 16, so he's got 6 times 4 is 24 valence electrons. But here's the main difference of the day. See that charge? See that -3? We didn't have any ions in the first lecture of VSEPR. If something is negative, does it have more or less electrons than it's supposed to? More, right? Because electrons are negative. This can only be -3 if there are more electrons than you expect there to be. If there's a charge and it's negative, then it just increases your count by that much. So what would happen if it was a cation? There would be less electrons than you thought if it were positive. All right, what's my grand total here? Anybody that can count? 32. So now moving forward, almost everything will be the same. We've got 32 valence electrons that must be in our image. Next step is to choose a central atom. I'll pick the one there's the least amount of, which is going to be that arsenic. And then bond the leftovers with single bonds. Elijah, you're leaving. And now you are forever in this video. Congratulations. You should come say hi on your way out so they know who you are. This is Elijah. He has 103 in the class right now. I lied to everybody. Okay. And then bond the leftovers with single bonds. All right, make sure you stop me if you're confused about any of yesterday's stuff. You're not allowed to. If you've watched the video from yesterday, then you're allowed to. You did? Didn't you just ask me if I had already posted the video from yesterday?
No, we're lying.
He did.
You watched VSEPR 1? Oh, what's your question?
Well, like, is it the AS and then you have 4 rounded because it has the O4?
You didn't watch the video. You're lying. All right. Now, remember, the next step is to make an octet everywhere. I'll tell y'all, the biggest issue y'all run into with VSEPR is trying to apply this number now. Don't do that. Ignore the blue. Add the octet everywhere. Right now, all of the oxygens are angry because all of them require 8. Each line is worth 2, so give each one 6 more. So here comes my lone pairs. Thank you. So arsenic already had his octet, and now everyone else has 8. If we're lucky, our picture will have a grand total of 32, so we can be done. Does it? I mean, it's not a trick question. Are there 32? Yes. Count them up. The lines are each worth 2. There is a grand total
32.
of 32, so we don't have to do anything else except shape, angles, polarity. So look it up if you need to. Shape, angles, polarity.
Oh, shape is,
It is tetrahedral.
yeah, that thing. It's polar.
Polar. No, it's not.
Non-polar.
It's non-polar.
Oh, wow.
It is tetrahedral.
Oh, wait, non-polar. Oh, yeah, non-polar.
Non-polar 109.5.
109.5.
Non-polar.
Non-polar.
Sir, why does it have to be in that order?
It doesn't.
So here
I have to just choose a way to teach it, though, man. All right, now remember, it's only non-polar because all of the exterior atoms are identical. If you look closely at your packet, you'll see that if any of these were not oxygen, while one of them still is, it would be polar because then there would be an unequal sharing. Dude, you're really bad stuff. All right, look here. Here's the other twist. All right, I've only given you one twist today, and it was negative charges make this bigger, and positive charges would make that number smaller. Here's the other new thing. If you draw an ion, like we just did, there's a charge on it. When you're done with your analysis, you are always required to put your image in brackets and put the charge outside the brackets. Or -3, whatever. You can write it either way. That's why I do it both ways regularly. Again, ions only. When you're done with the Lewis structure, add brackets and throw the charge out there. It's easy. It's a simple thing, but don't forget to do it. All right, let's draw some cards. Stop it, please. For those of you at home, the screen now says oxalate, so let's draw it together. All right, let's go over to cluster 6, seat 5. Hey, 6-5, what is the formula for oxalate? Do you have a polyatomic list? Oh, well, then you know what?
Can I have one?
Super gift for you.
A super duper duper gift?
What is oxalate? Say it out loud for everybody. C2O4, he said. C2O4 -2. Does everybody see that? Well, look harder. Point it out. If you can't see it, have someone next to you point it out to you. All right, let's go get some valence help because we need a cat. Let's go to cluster 3. Seat 4. Hey, 3-4. What is the valence count of 2 carbons? 8 is correct. It's 4 twice. Let's go over to cluster 2. Seat 1. Man, it's really been crazy lately. What is the valence count of 4 oxygens? 24. Because 6 times 4 is 24. Let's go over to cluster 6. Seat 4. Yeah, I found you that time. What is this going to make it bigger or smaller by 2? Bigger, because negatives means that there are more electrons. So if you sum them up, you'll get 34. Now, this molecule is a little weird for a couple reasons, and that's going to happen. You're going to run into examples that don't fit perfectly in the little boxes I've tried to draw for you in regard to steps. But do you see how there's less carbons than oxygens? All right, well, let's put both carbons in the middle then.
Is it one of those?
And we've got 4 oxygens left, so let's just add them symmetrically. All right, so let's just go. Something like that. Now, if you went left and up and right and up or whatever, it's fine. Just make sure each carbon possesses 2 oxygens. Let's go over to cluster 3, seat 1. Hey, 3-1. Is anything stable? Nothing is, right? Because there's no hydrogen. Remember, hydrogen only needs 2. But everything wants 8 and nothing's there. Let's ignore the 34 and give everybody an octet.
Oh my gosh.
Everybody okay with the octet? You see that there's 8 everywhere? Don't suffer in silence. All right, well, here we go. There's our number. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. Ruh-roh. We're way off. Let's go over to cluster 3. We're picking on y'all today. Seat 1. Hey, 3-1. What is the, can you tell me the rule for fixing it? Erase 4 dots, add 1 bond. Now, careful. All right, remember, if possible, 2 of them will always come from the central. And then you'll pull from an exterior. So I'm going to pull 2, 3, 4. All right, you could have gone up if you wanted to, whatever. All right, so 1, 2, 3, 4. Erase 4 dots. Add 1 bond. Now, if you haven't caught on, every time you do my trick, it reduces your count by 2. So we were at 38. We did the trick. So now we'll be at 36, which is still no good. So erase 4 dots, add 1 bond. So let's go symmetrical. Let's go to the other central atom. 1, 2. Y'all want to go up or down? Ooh, up. That's pretty. Erase 4 dots, add 1 bond. Now, it's fine if you go down instead of up. Those are called resonance structures. More on that in January, yeah. You want to try to remove it as symmetrically as possible, yes. All right, but at this level and what we're doing, I don't care which one you remove, as long as you are making everything happy. And now there is a grand total of 34. Now, I see some of y'all looking for shapes, polarities, and angles. We're not going to charge that on this one because this shape is a little bit outside of our honor scope. So let's ignore that for this one. But
let's go to cluster 3 again. If it's 3 in a row, that would be incredible. Cluster 3, seat 2.
hey, 3-2. There is something important missing from my drawing. What is it? You do know, though, because I didn't teach it until today. Brackets! Brackets! If you draw an ion, your Vesper-Lewis structure must be in brackets with the charge on the outside. Can you see that? Now you can see that. How are we feeling? Frickin'?
We're only supposed to have one of the things.
Pyramid thingies, like the trigonal pyramidal? Yeah.
We're only supposed to have one of the elements.
You're gonna watch that other video, right? That's gonna happen. Did you say no? I'll come see you in a second if you have a question. Hey, here's the last problem of the day. Do a full analysis. All right, this one you can do the shape and angles and everything. I know, because I told you that one's outside of our scope. Because I want you to be able to draw everything. They're doing nitrite. At home, they're doing nitrite.
Hey, DJ, what's nitrite again? NO -2? NO2, what's the charge?
So does it have a negative charge?
Is it, what is negative? One charge? -1. Christ, all that.
So it's not that, but this one.
Thanks, Nicholas.
How many does negative have? 1.
Oh, wait.
Because everything's 6
Wait,
flat.
12.
So that is 6. So that's 18.
Now this one's also
Oh, yeah.
Now you take the 10. There's only 2 more options.
the trigonal pyramidal is only bonded to 3 things.
No, we need 3. It's a bent one.
It's bent.
Only bonded to 3 things.
Okay, so now it's bent. So now you make everything. So now you make everything.
Oh, yeah.
What is nitrite?
I said that first, Deacon. I did first.
4, 6, 8.
Aggregates 5. Nitrogen has 5 valence electrons. Why are you putting 6 on nitrogen? 5, 6, 7, 8.
The line is 2.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, so
We
you
have that done.
to erase 4.
Erase 4, add a bond. No.
Yeah. Erase 4, add 1 bond.
Where are you erasing?
I just took 2 on the outsides of both oxygen.
Wait, let me take that one.
So do you have to take 4 away from one specific one, or can you take 2?
Try to go central and then exterior.
Or it has to be a central and then an exterior.
Yeah, always start with the central if there's a central.
That one.
16.
No, then you have to make the bracket negative. Just negative.
You gotta do the name and stuff too.
Yeah. Okay. So it's a bent.
Put in parentheses 2 unpaired.
Bent polar with
109.5.
It is 1.5.
Okay.
So you're giving the good stuff and you stop calling people.
Wait.
Same people.
Wait, there's two.
Sir, how do we know the difference between the 1.5 and 1.20?
The what and what?
For vents, for 120 and.
Oh, it's because it's based off hybridization. I haven't taught you that yet.
So we just put the 1.20.
109.5.
It's not bent. The answer to this is not bent.
Alright, trigonal. Linear.
No, I need what do you mean 30. Sir, how in the world is it not that?
It's linear.
Oh, yeah, it is.
Parts of it, yes. Like this, like to be trigonal, it's fine if you can add one bond. Right? But if those three things out, it's different. One of them different. It's full. They're all the same. That part doesn't matter.
There's 18.
All right. Oh, you raising? I went systematic. Like I went through the exact same steps.
Shame on you, dude.
I don't know when to and when not to. It's just when I looked for a central atom, I saw that there was no one thing to prove. I had two of something and four of something. So I picked two of something, and then I built the others around it. When you went to this one, you take only one thing to put in the middle, and then I built the others around it. So it's systematic.
It looks like you typed it.
All right, let's see how you did. Stop me if I do something weird. Nitrogen is in group 15. Oxygen is in group 16, but there are two of them. The negative will increase my count by 1 for a grand total of 18 valence electrons. All right, there's only one nitrogen, so let's put that dude in the middle and bond the leftovers to him. You should have ignored the 18 and made everybody happy. Now look for a second. I'm about to do a shorthand that you don't really have permission to do yet because I don't think you're good enough at this. You should draw dots, but if you decide you want to shorthand like a pro, you can draw your lone pairs to look like that, but only if you're going to think about what you're doing. Like if this was my final drawing, it's not because there's more than 18. But if this was the final picture and a question said, how many lone pairs are there? Because my test might ask you that. How many lone pairs are there on your molecule? Well, if you draw it like that, you might confuse yourself because lone pairs are the dots. So you've got to be careful. The answer would be 1, 2, 3, 4, 5, 6, 7, 8. Because by definition, lone pairs are unbonded electrons. These are shared pairs, bonded electrons. Anyway, I'm just cheating because it's time to get lazy. But we need 18. Everyone now has an octet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That is the wrong number. Erase 4 dots, add 1 bond. I'm going to always take 2 from the central. Y'all want to go left or right? Ooh, left.
Right.
Stupid. So, erase 4 dots, add 1 bond. Now there's 1, 2, 3, 4, 5, 6 lone pairs, and 1, 2, 3 shared pairs would be a way to say it. All right? But there's a grand total of 18. Everybody has an octet. Ooh, brackets, very good. Yeah, make sure you've got brackets, right? Because it's an ion. Yes. No, you could put just a positive. You're taking charge of. Yeah, no. I need to know whether it's negative or positive. Yeah. Hey, before I do the shape and all that stuff, here's a fun question I could ask. Which bond in the image is the shortest? Which bond is the shortest?
The one on the right.
None of them.
No, one of them is.
The one on the right.
The double bond is. We learned on our intro day that the shorter the bond, the stronger the bond. And you can find elsewhere in your packet that double bonds are stronger than single bonds, triple bonds are stronger than double bonds. That's very logical. So if this is the strongest bond, it must be the shortest bond. Yeah? This is going to be linear with 180 degrees and non-polar.
Hey, there's a hyphen in there.
It's not bent. Bent requires 2 lone pairs on the central atom. All right? Linear doesn't have that requirement. You have survived semester 1 of my class. Well, maybe.
Not officially.